Hello everyone. Today I am going to be teaching you about isotopic signatures in teeth and bone. So, what are isotopes? Isotopes are different versions of the same element. They have the same number of protons but a different number of neutrons. And it is this difference that makes them so useful for research. As you can see to your left, there are two atoms of carbon. One is carbon 12 and the other is carbon 13. The only real difference is carbon-13 has one extra neutron. Our bodies actually absorb those differently depending on the foods we eat. So if you measure the amount of carbon-13 in somebody's teeth or bones, you can learn something about their diet and even where they lived thousands of years ago. But before we get into how all that works, we first need to look at the two main kinds of isotopes scientists study: stable and radioactive. Not all is- Not all isotopes behave the same way. Some are radioactive, which means they break down over time. These are useful for dating fossils and artifacts, like using carbon 14 to figure out how old something is. But for the sake of time, we're going to focus on stable isotopes, which don't decay but rather stay locked into the body once they are absorbed. That makes them perfect for studying things like diet and movement because chemical signatures you get from stable isotopes reflect what someone was actually eating or drinking during their life. For example, carbon 13 is stable, and that's what we'll use to figure out what kinds of plants someone ate. Oxygen isotopes, like O18, help track where someone got their water, and that's where we start seeing movement. But we'll get more into that later on in the lesson. Alright, tooth enamel versus bone. Now that we know which isotopes we're looking at, let's talk about where they show up in the body. As you can see here, we're starting off with tooth enamel, which is the hard outer layer of your teeth. Enamel forms during early childhood, and once it's formed, it doesn't change, it doesn't grow, remodel, or update. And just to clarify, this comes from permanent teeth, not baby teeth. In humans, it usually forms between the ages 6 and 12, though it varies across different animals. If you look at the timeline, you can see that enamel formation happens early on, and it stays frozen in time. That's why it's so useful That's why it's so useful. It's like a chemical snapshot of what someone was eating and drinking during their childhood. So, when anthropologists study enamel from ancient teeth, it's like they're getting a chemical snapshot of what life was like when that person was still a kid. Unlike enamel, bone isn't locked in place, but actually changes throughout your life. Bone is constantly remodeling itself. This means that the chemical signals in your bones reflect what you were eating and drinking more recently in time. If you look back at the timeline, you can see how bones keep updating as you get older, while enamel stays fixed. So while enamel gives us a snapshot of early life, bone gives us an update of adulthood. By comparing both enamel and bone from the same person, we can see if something's changed in their life. That could be a shift in diet, or even a shift in a different environment. And we'll get to that. We'll get to that soon. Carbon isotopes and diets. Now, let's talk about how stable isotopes help us figure out what people were eating. Plants absorb carbon differently depending on how they photosynthesize. This creates two types of groups: C3 plants and C4 plants. As you can see here, C3 plants include things like fruits, vegetables, nuts, and most trees. These take in less carbon 13. On the other hand, C4 plants like corn, millet, and sugarcane take in more carbon 13. That difference shows up in bones and teeth of people who ate those foods. This means if we measure the carbon isotopes in a fossil and find high levels of carbon 13, we can guess that that person was eating more C4 based foods like corn. This is one of the main ways we figure out ancient diets. So how do these plant signals actually end up in our skeletons? Well, it starts off as food, gets digested in the stomach, and goes through your bloodstream. And through your bloodstream, it gets absorbed by your bones. Oxygen isotopes and movement. So now we're switching gears from food to water and how it can tell us where someone lived. The key here is oxygen isotopes, specifically oxygen 18. Just like plants absorb carbon, water contains different levels of oxygen isotopes depending on where it came from. As you can see on the map, elevation, climate, and region all affect the isotope levels in local water sources. When a person drinks water, the oxygen isotopes get absorbed into their body and end up in their bones and teeth, just like with food. So if we analyze those oxygen levels, we can start to figure out where that person lived, and lived based on the water they consumed. So here's where things start to get interesting. We can actually use oxygen isotopes to see if someone moved during their life. Remember, enamel forms in childhood and locks in those early oxygen levels. Bone, on the other hand, keeps updating as we age. For example, someone might grow up in the highlands, where water has more oxygen 18, and later move to the lowlands. That shift would show up in an isotope comparison. So let's now look at a real case study where stable isotopes helped uncover a hidden story. Back in 1999, archaeologists found 3 Inca children buried near the summit of a volcano in Argentina, over 22,000 feet up in the Andes. These were ritual sacrifices, preserved by the freezing conditions. The most well-known is the Lulaco maiden girl, around 15 years old. According to a peer-reviewed study by Wilson and others in 2007, the hair from the mummies provided detailed genetic, diamorphic isotopic information, meaning they could track changes over time. This gave researchers an unprecedented look at the last years of these children's lives, what they ate, where they went, and even signs of social status change, all from analyzing their hair. Researchers tested the maiden's hair for stable isotopes of carbon, nitrogen, and oxygen, and hydrogen. Because hair grows over time and doesn't change once it's formed, each section preserves a chemical record, kind of like a timeline. They found that her carbon and nitrogen levels started to rise about a year before she died. That means she began eating more elite foods like maize and meat, probably prepared for a sacrifice. They also noticed changes in her oxygen and hydrogen isotopes, showing she was moved to a much higher elevation in her final months. Even more amazing, a small bag with her contained cut hair that perfectly matched her own. It was likely trimmed about 6 months before her death, possibly as a part of a ritual step. As authors put it, serial segments along any hair shaft can yield diamorphic information for the final months and years of a life history. This kind of detail would be impossible to recover without isotopic analysis. This case study shows how stable isotope analysis can do more than just tell us what someone ate. It can also help reconstruct the final chapter of a person's life. From the maiden hair alone, we learned that her diet changed, her social status likely rose, and she was moved across regions, all leading up to her ritual sacrifice. It fills in the gaps in historical records, giving us a personal human story from over 500 years ago. And it shows how anthropology, biology, and chemistry work together to reveal not only just facts, but real life experiences. That is the end of my presentation, and I hope you learned something new. Thank you.